Determinants of a matrix have many uses. Let's start with the 2 by 2, and this is only going to work for the 2 by 2. But let's say we wanted to take the determinant of A, B, C, and D. We just do a little crisscross rule, so we're just going to say AD minus BC. And if we do that, then we're going to get the area of, say, the parallelogram that is formed here by those two vectors. We also have a quick trick for the 3 by 3, but this is only going to work for the 3 by 3. So let's say we wanted to take the determinant of A, B, C, 1, 2, 3, and then 4, 5, and 6. Well, what we're going to do is sort of rewrite that again over here. A, B, C, 1, 2, 3, 4, 5, 6, kind of like you would for the cross product situation. So in order to find the determinant here, let's start by drawing some lines. We're going to start with the very first entry and draw some lines downwards like this. And we want to kind of be careful to line everything up properly. And then we're going to have some plus signs over here at the top. So it'd be something like plus, we're going to multiply A times 2 times 6. So we're going to get 12A here, 12A. And then plus B times 3 times 4 is going to give us another 12B. And then here's another plus, C times 1 times 5, so we get a 5C. Now let's repeat the same thing for the bottom side, the left side entry here. We're going to start here, draw our 3 sections, and then we got a minus, and a minus. So we'll do minus 4 times 2 times C, it's going to be minus 8C. And then we have minus 5 times 3 times A, so that's minus 15A. And then we have 6 times 1 times B, so that's minus 6B. And again, you kind of want to line this up carefully, maybe with some like graph paper or something, so it's a little neater. But there we go, we've got the determinant. Well, if the 2 by 2 gave us an area, it makes sense that we might be able to get a volume out of this 3 by 3 over here. Something like this. Nice. Well, what if the determinant isn't a 2 by 2 or a 3 by 3? We can also use a cofactor expansion method. This will work for any square matrix. So let's say we want to find the determinant of A, and usually that means that we'd have to do something like this. We got a little formula. A11, C11, and then we'll say like, this is meaning row 1, column 1. And then we'll have A12, so row 1, column 2, and then we have this cofactor of C12. And then we can sort of generalize this slightly more. So A1, this is the first row. You could pick any column at this point. You got to add them all up, and then you have your cofactor that goes along with that. Let's look a little closer at the C11. First, we need a -1, and then we're going to put that to the power of 1 plus 1. And then we need to multiply this by the determinant of A sub 1, 1. So what this really just means, it's kind of more like C of RC, it's the cofactor, is going to be equal to these little things right here. They're going to be equal to this general idea. We take this -1, and then we're going to add on top the row plus the columns. So whatever row and column we're sort of choosing. I'm going to go more into detail later to show you an actual example, but we kind of need to know this stuff. So then we got to multiply this by the determinant of the A and the RC. It doesn't really make a lot of sense when you write it down, but the idea is we're trying to eliminate the row R and the column C. So the determinant after you've eliminated the row and the column that you've chosen. So well, let's try to decipher what all this really means. Let's look at this matrix here. And I'm going to put in some sign factors. So we'll start with this plus, and then I'll do a little checkerboard. Minus, plus, minus, plus, minus, plus, minus, and there's a plus in between. Those are the sign factors. Now, how do we get those sign factors? It's from this -1 to the power of, well, whatever R in the row, or row in the column we are. So here it'd be 1 plus 1, it's just going to be -1 squared, so that's just a positive. And then, you kind of keep doing that, but it gets a little crazy. So I prefer to look at it more like the sign factors and then just kind of be familiar with this formula, but this is sort of the faster method, is to put a checkerboard of plus and minus signs all everywhere. Now we're going to apply our formula, and we're just working with the first row, and when we do that, we're going to get the determinant. So let's start with adding this plus a. We have the plus a here. So that takes care of this thing and that, and then we just have to multiply this by the determinant of whatever is left after we've eliminated row 1, column 1. So we're going to get rid of all that, and we're left with this little piece right here. So we'll put the determinant of 2, 3, 5, and 6. And you don't put these positives and negatives in there, just on these coefficients here. Next, we can pull out our b. It's just going to be right here, so you get a negative b times the determinant after we've eliminated the first row and the second column. So we'll take the determinant of 1, 4, 3, 6 here, and then we could pull out the c and do the plus c, and then times the determinant of, well, 1, 2, 4, 5. 1, 2, 4, 5. So there we go. Now you can see how this matches up just to the formula quite nicely. Another good method is to use echelon form. If you could somehow reduce your matrix to a triangular shape, such as the upper triangular or the lower triangular, you could easily find the determinant, because it's just going to be a times b times c, a times b times c, a times b times c, just going along this diagonal here. So that's pretty nice and easy. You just have to follow some rules. The first thing is you have to make sure that if you do replacements, well, then you actually have no change in the determinant. So replacements are really good to make when you're trying to get down into the triangular form. Or you could try doing some swaps, but the thing is you have to keep track of them, because that's going to get you a negative determinant. So you're going to need to reverse that once you get to the final answer. But then the third one is you could also try doing some scaling. If you scale one of the rows, then your determinant at the end, you're going to need to divide that by what you just scaled it. Otherwise, it's going to be a scaled determinant. So this is how you can get back to your determinant of a, by reversing the movie making. Negative determinant, or dividing that determinant and getting your determinant of a back. This is if you need to make these moves in order to get it down into the triangular form. Another quick trick is if you can spot some row or column multiples, then that's nice, because the determinant is just going to equal 0. So if you do some row operations, and you could somehow reduce it down and find an all 0 row or column, then look at that. Boom. You get all 0 there, all 0 there. You just pull them out and do the cofactor expansion, and then you get a determinant of 0. Let's make a note of a few more properties of determinants. We should know that the determinant of AB is equal to the determinant of A times the determinant of B. Also, if we were to scale our matrix by some k, then we will get the determinant of A, but it's actually going to be scaled by this k to the power of n. So basically k to maybe the third power if you have 3 columns. Another property is that you have the determinant of A transpose being equal to the determinant of A. And we also have the determinant of the inverse of A is equal to 1 divided by the determinant of A. Now let's try applying Cramer's rule. I've set up this matrix equation here. We have this matrix A and this x vector, and it's going to be equal to this b over here. Well, let's say we want to try to solve for this x. So we could actually set up both of the equations at the same time. We're just going to go x1, x2, and then this is going to be equal to, we'll start with the determinant of a sub 1 over here, and then we'll go ahead and divide that by the determinant of a, and we'll kind of do the same thing over here. So the determinant of a sub 2 over here, and then divide that by the determinant of a. So what are these sub 1s and sub 2s? Well, basically, we're going to be creating a new matrix over here, where we're going to replace this B and put it in, well, whatever x we're trying to solve, so this is this one here, it's corresponding to this pivot, and this one corresponds to that pivot. So we're going to go ahead and plug this B into that first column. So we'll put it in here. We got B1, B2, and then 1, and this A2 over here. So that's what A1 is. So we're going to divide that by determinant of A, and that's basically going to get us our x1 pretty quickly. We can also do the same thing for this x2, so let's just go and plug that in there. And again, we're going to take our B, and we're going to find the second variable that we're looking for. We're going to find its pivot, and then we're going to plug in the B to that column over there. So we're just going to say we have the B1 and the B2 on this side, and then the rest is just going to be the same. So we have A1 and 1 over here. We'll divide that by the determinant of A, and there we go. We've solved for both x1 and x2 pretty quickly. Now let's consider some transformations. Let's say we have this matrix A that's giving us a transformation. Well, we can determine that the determinant is equal to 6. And if we know that, then we know that the transformation that this would apply is going to scale areas by 6. So we could prove that by drawing a little square here. We'll call this 0, 0. This is 1, 0, 1, 1, and 0, 1. And here we can know, well, the area is equal to 1. But if we were to try to apply a transformation here with this matrix, then we would get something more like this. It's going to be like, maybe here's 0, 0, but here it would be 2, 0, yeah? And then over here we would get 0, 3, and then here we would get a 2 and a 3. So you can see that the area here is equal to 6. Let's make a note that if A has a negative determinant, then that's actually going to flip the orientation of the object that you're going to transpose. But if you have a plus determinant, then that's going to preserve the orientation. As you can kind of see here, the orientation was preserved. Lastly, let's consider this little matrix here. We can see that if we multiply here diagonally, we're going to get a determinant equal to 0. But that still gives us some information. It shows us that this is actually a subspace. And so we can see that this A actually spans a two-dimensional subspace of R to the n. And there we go. So determinants can actually give us a ton of information based off of what we're trying to do with them.